In this video, I'm going to talk about a two-sample comparison of means using a confidence interval and also a hypothesis test. So the data we're going to look at concerns a sample of lizards, and we've got two variables, one of which measures the length of the lizard's horn. This is a horned lizard, and the other variable is a categorical variable that is measuring whether the lizard survived or was killed by a shrike, which is a type of bird. What I like to do anytime I've got a categorical variable is to create a factor variable from it, and that allows me to order the levels of the categories. And this is useful particularly when graphing the data. And so if I use the factor function and then specify the levels, I can put the levels in whatever order is most meaningful to me. So I'll do that, and then I'll create a couple of histograms so that we can see what the data look like. And we can see that the distribution of the horn lengths for the living lizards is from kind of a little bit below 20 up to almost 30. Okay, so there's the distribution there. Looks relatively normal. And then the lizards that were killed by shrikes, the distribution of their horn lengths, it seems to be, in general, they seem to have shorter horns than the living lizards. So their distribution goes down from like 15 up to kind of 25, 26, 27, somewhere there. So it appears, at least from these multiple histograms, that the living lizards tend to have longer horns than the killed lizards. And that kind of makes sense. The shrikes probably find it a little more difficult to kill a lizard if it's got a longer horn. The lizard is using the horn as a defensive mechanism. Okay, the other thing that happens here is we've got this weird warning message that it's removed one rows containing non-finite values. So let's investigate that a little bit further. Let's look at the entire data set. So I'm just scrolling up here just to see if I can find, okay, there it is. That's the problem. Okay, the 105th lizard in my sample has a value of NA, not applicable, for its horn length. So for whatever reason, the researcher, when it came to lizard 105, didn't record the horn length for that particular lizard. So we're not going to be able to use this lizard in our analysis. So it's a little bit cleaner if I can just remove that from my data set so that I don't get any of these error messages or warning messages in R. So I'm going to do that using this filter function. And what this does is it filters the original data set, and this code here, exclamation mark with an equal sign, this is read by computers as meaning not equal to. So what I'm doing is I'm filtering this original data set, and I'm keeping everything that has a horn length not equal to NA. So in other words, I'm keeping everything except that lizard number 105. Okay, so we've got a good data frame to work with now, and I can calculate a confidence interval for the difference in population means in the two groups. Okay, because that's what we're interested in here. We saw in the histograms that there appeared to be a difference in the distribution of the horn lengths, and if we can think about the population mean horn length for living lizards and killed lizards, the question that we're trying to answer here is, does it appear that there's a difference in the population means? So one way to address that question is with a confidence interval. I could calculate the difference between the sample means and use that information to calculate a confidence interval for the difference in the population means. Okay, so a lot of steps here. We can calculate the sample mean for the living lizards. It's 24.28, and for the killed lizards it's 21.99. Look at the sample standard deviations. Those are roughly the same. In the living group it's 2.63, in the killed group it's 2.71. The two sample sizes, there's 154 living lizards and 30 lizards that were killed. And I can combine those two sample sizes and then subtract 2 to get the degrees of freedom. And then I can combine this sample standard deviations using this formula, and that gives me the pooled variance. And then I can use that pooled variance to calculate the standard error. And then if I want to calculate a 95% confidence interval, that's equivalent to a 5% significance level. So I'll set alpha as the significance level, and then I'll use that information to calculate the critical value. So the critical value, if I'm doing a 95% confidence interval, I can think of that as having 95% contained within the interval, and then there'll be 5% spread between the two tails, so 2.5% in the lower tail and 2.5% in the upper tail, and so my critical value will be the 97.5th percentile of the t-distribution with this number of degrees of freedom. So I can calculate that, and then I can put all these pieces together. So the lower bound of the confidence interval is given by the difference in the sample means minus the critical value times the standard error, and then the upper bound of the confidence interval is given by the difference in the sample means plus the critical value times the standard error. So there's my confidence interval. We can say we're 95% confident that the difference in the population means is between 1.25 and 3.34. Okay, so that's one way of addressing this question of does there appear to be a difference between the living lizards and the killed lizards with respect to their average horn length. The other way to address that question is to do a hypothesis test for the difference in the population means, and we use a two-sample t-test to do that. So first thing we can do is, first step of any hypothesis test is to state the null and the alternative hypotheses. So the null hypothesis is that the lizards killed by shrikes and living lizards do not differ in their mean horn length. In other words, the two population means for the two groups are the same. And the alternative hypothesis is that lizards killed by shrikes and living lizards do differ in their mean horn length. So the two population means are different. So this is a two-sided or a two-tailed test that we're going to do here. So that's step one. Step two is to calculate the test statistic. So to do that, we're going to specify the null value for the mean difference. So that's 0 in this case. And then the test statistic formula is given by the difference in the sample means, subtract the null hypothesized value divided by the standard error. So we'll do that calculation, and we get a test statistic of 4.35. Step 3 is to calculate the p-value associated with that test statistic. So we're doing a two-tail test. So our p-value will be the tail area to the right of the absolute value of the test statistic times 2. So this function here, pt, gives us the area to the left of the absolute value of the test statistic. So if I subtract that from 1, I'm going to get the tail area to the right, and then multiply that by 2 to get my p-value. So there's my p-value, comes to 2.27 times 10 to the minus 5. Step 3 is to No, that was step 3. Step 3 was calculating the p-value. So the p-value is 2.27 times 10 to the minus 5. Step 4 is to make a decision and draw a conclusion. So the decision rule, as with every other hypothesis test, it's always the same. Reject the null hypothesis in favor of the alternative if the p-value is less than the significance level. So 2.27 times 10 to the minus 5 is smaller than 0.05, and so we do reject the null hypothesis in favor of the alternative in this instance. So our conclusion is that lizards killed by shrikes and living lizards do appear to differ in their population mean horn length. So in other words, the two population means do appear to be different. Okay, so that was a lot of work. It's good to go through those hand calculations maybe once or twice just to get used to what's going on and to understand in a little more depth what we're doing here. But as soon as you're comfortable with that, feel free to go ahead and just use the t.test function, because that will give you the results much more quickly. The danger, of course, with doing that is it gives you the results, but if you have no insight into where the results are coming from, it can be a little harder to process that information. So that's why I find it helpful to go through all this first. But once you're comfortable with that, then we can use this t.test function and get the answers straight away. So I'm just going to dwell a little bit on the code that we're using here, because this is something that we've not really come across before. So I'm using a tilde function here. So the tilde, you'll find it on the keyboard in the top left corner of the keyboard. And the way this piece of code is used is that the variable on the left of the tilde is the response variable in the analysis that we're doing. So the response variable in this case is the horn lengths for the lizards. And then on the right side of the tilde, we put the predictor variable. And in this particular case, we can think of the predictor variable as we're trying to figure out whether there's a difference between living lizards and killed lizards. And the categorical variable that is telling us which type of lizard it is this survival variable here. And then finally, this var.equal argument, we need to set that equal to true in this case, because this test that we're using makes an assumption about the variances in the two groups. So it's assuming that the variances in the two groups are approximately equal in the population. And so to assess that visually, we can think about the spread that's illustrated by this histogram for the living group and compare that with the spread for the horn lengths in the killed group. And if those are roughly the same, then it's okay to make this assumption. And then if we use the t.test function to do the confidence interval calculation and the hypothesis test calculation, we need to set that argument equal to true. In the next video, we'll use a variation of this test where we're not making that assumption. We can also look at this numerically in terms of the sample standard deviations. The sample standard deviation for the living group is 2.63 and for the killed group is 2.71. So those are reasonably close to each other. So it's reasonable to assume that in the population the sample standard deviation in the population the standard deviations are the same. If the standard deviations are the same, the variances are the same. I think the book talks about a rule of thumb here about these standard deviations. I think it talks about if the difference in the standard deviations in the two groups, if one is 3 times larger than the other, then this assumption is perhaps not reasonable. But in this case, these standard deviations are almost the same. Okay, so once we've got all that code written out, then we can run the function, and that does all those calculations that we went through. So here's the test statistic. There's the degrees of freedom for the t-distribution that we're using, and here's the p-value for the two-tailed test. Here's the alternative hypothesis that tells us we're doing a two-tailed test in this case, and then here's the 95% confidence interval, and then here's the two sample means in the two groups. Okay, so that's how to do a two-sample comparison of means if we're assuming that the variances in the two groups are the same. And we looked at a confidence interval, and we looked at a hypothesis test. In the next video, we'll do something similar, but it'll be for an example where we can't assume that the variances in the two groups are the same.